Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this thermomechanical analysis of fixed beam step-by-step procedure. Now I have just taken a simple beam of 1 meter length and 0.1 meter and 0.1 meter height and width I have taken. And I have taken a material property of steel with Young's modulus of 210 gigapascal and Poisson ratio is 0.3. And thermal expansion of our material is 12 e power minus 6 1 by Kelvin, and density is 7860 kg per meter cube, and thermal conductivity is 40 watt per meter Kelvin. Now we'll see the boundary condition. So our boundary condition is, in thermal analysis, one side we have 100 degrees Celsius and other side we have 200 degrees Celsius, and in structural analysis both the side we are fixing completely. Due to the thermal difference, it will start to expand, but the expansion is arrested by the fixed support. Due to that, it will develop the stress. Now we'll see how much the stress is developing. So first, now this thermomechanical analysis we are going to solve by using a Salome. Please subscribe my channel for more videos and click the bell button for notification. Now we'll move into the problem. First go to the Salome. I opened Salome 2022. First go to the geometry model. Now we are in geometry model. Now we can model our geometry. Our geometry is very simple. Just 1 meter length and 0.1 meter and 0.1 meter width. For this, I'm going to model it as using a primitives box. This is 1 meter. These two are 0.1 and 0.1. Apply and close. Now I have modeled the geometry. Then we will create the groups to apply the boundary conditions. So select this box one. Go to new entity. Groups. Create groups. Now we want to create the face group. So fixed to 1 I am giving, just apply, and other one is I am just naming as fixed 2. Same group I am going to use it for thermal also. For fixed 1 I am going to apply 100 degrees Celsius. For fixed 2 I am going to apply 200 degrees Celsius. Now I have created these two groups. Now we'll save this geometry. So this is the first model. I'm just saving here. So I have modeled geometry and I have created the groups. Now I have saved it. Now we'll move into the meshing model to create the mesh. Just move into the mesh model. Now we are in the mesh model. Select this box one, mesh, create mesh. Now in this I'm going to create tetra element. So use the NetGen 1D, 2D, 3D. I'm going to use the simple parameter. Here we can specify the local length. I'm giving 0.02 as the local length. Just say OK and apply and close. Now we have to compute the mesh. Right click here and compute it. Now we have generated the linear element of tetra element. So this mesh is enough. Now you can check here groups also. Now groups also imported into the mesh. Now we can go for aster study to create the setup. First, in this case, how we are going to solve is, we are going to create the setup for thermal analysis and we are going to solve it. After solving it, we are moving into the mechanical analysis. Now we just go to the aster study. In the previous tutorial, we have solved by using an assistant to create the setup. In this case, I am going to create the setup one by one. Just add a stage. Now we can create the setup by using these tools. Just first we have to read a mesh, select this mesh one, MED format, just apply and OK. Now we have read the mesh. Now just go to the assign finite element. So this is actually finite element analysis. Edit, everywhere, here thermic, and this is the 3D model. Just OK. Apply and close and OK. Now we have created the reader the mesh, we have assigned the model. Now we have to define the material. First to define the material, any name we can give. I'm just giving a meter. So in this material property, this complete data we have to taken into the model. So just linear isotropic. First what we are going to do, we are going to do with the so first we'll add a thermal material property, then we'll do the mechanical material. Thermal conductivity is required to solve the linear static conduction problems. So I just taken 40 is the conductivity, just apply and OK. Then we have to assign this material property to the model. For thermal analysis, the conductivity, linear static analysis and linear static thermal analysis, it require only the conductivity. I have given only the conductivity. Then we'll assign the material to the mesh and model, to everywhere the same material property. Just apply and OK. Now we have assigned the material property. Function and listers are not required. Then we have to move to boundary conditions. Just go to move boundary conditions load, assign thermal load. Here we just want to assign only temperature boundary condition. Here you can see enforce temperature, edit. We have a group of elements, fixed one. We have to give a temperature in the Kelvin. So 373 Kelvin. Then again plus edit, group of element, fixed to, just OK, temperature 473. So two temperature values we have given here, just apply and OK. Now we have defined the load. Then we just want to define the solver. For that, just move into the analysis. Here you can see thermic solver, linear thermal analysis. So we just want to include the load here. Load, just say OK. Is there anything we just want to include? No. Just apply and OK. Now we have defined the solver. Then we'll save the results. Just go to output, set output results. Just locate the folder where we want to save. Thermal.rmed. Just save. Just include this result value. Just outjump make it as, just save OK. In MED format, just apply and OK. Now we have defined the solver for the thermal analysis. Now we'll solve this data and see the thermal data, thermal results. So just save this file, goes to history view. Just simply run this case. Now it started solving. Yes, now it is solved. Now we'll see the results. Just right click here, go for post processing. So this is the temperature data. So one side you can see it here, 373 Kelvin. And other side it is a 473 Kelvin. The conduction is happening between these elements. So this is the thermal data which is correct. Now we'll due to this we'll see the stress values. Due to the temperature difference, the material start to expand. That expansion is arrested due to the fixed support. So due to the fixed support, it generates the stress. That value we'll see by using the structural analysis, by coupling thermal and structural analysis. Now we just move into the aster study again. Now in the same case, we have to add one more. So mesh we are reading it, model definition. We have to define one more model, that is model st. Just it's better to differentiate the previous model and current model. I'm just giving model st, finite element everywhere, mechanic 3D, just OK, apply and OK. So structural analysis model I have defined, and material. So previously we have defined the material, only the conductivity. Now we have to include Young's modulus and Poisson ratio and thermal expansion data. Now just go here, just edit it, edit the same material property. Now just click this linear isotropic value. So Young's modulus is 210 e power 9 and Poisson ratio is 0.3. Density is not necessary and thermal expansion is essential. So just 12 e power minus 6. So all the required data we have input we have given. Just give OK, just apply and OK. Now you can see it here. So Young's modulus and Poisson ratio and thermal expansion data we have included. And same material property is assigned to here. Assigned to here. Now just apply and OK. So while defining the so model we have defined, material we have assigned the material. Again go to assign the material. So we have to define one more material assignment, that is field mat st. So just coming back again. Yes, so we have to model. So here we have to choose the model st, assign everywhere, same material. After assigning the material, so external state we have to define. Just go to edit. So external state is a temperature and reference value is atmospheric value of 293 Kelvin. So assigned to everywhere. So transient value is thermal data. Just say OK, just apply. So here you can see a material st we have defined. Just say OK. So after that, so we have assigned the material. Then we have to define the boundary conditions. Just go to BC load. So assign the mechanical load. So load st will name it for easy understanding. Now we have to apply a fixed support. So enforce the degree of freedom. So edit. So we have a group of elements, fixed 1 and fixed 2. Both has to be fixed in the displacements. That's it. Just say OK, just apply and OK. Now we have defined the boundary conditions and loads. Now we'll define the solver. Just go to the analysis, static mechanical analysis. Here you just choose the material as. So material data is field MAST and model is the model ST, and here loads we have this load ST. Just say OK. Nothing we need to define, just apply and OK. Now we have defined the Roslin as a static solver. Then we have to save the output. Just go to the set out. So we just want to calculate the stress also. For that, just go to the post processing, call champ, use the same data. So we have to Roslin, we have to use it, constraint and criteria. So sigma element and sigma node. Here just add SAEQ no and SAEQ node. So just apply and OK. Now we have calculated this stress data that has to be saved in the output file. Here just click it here, just add one more file, edit, mesh, result is the calc meca, taucham, make it yes, just OK, just apply and OK. Now we have defined the structural solver. So we have coupled the thermal and structural solver in step by step. Now we'll solve this case. The same output file name I have given. Now we'll solve this data. Just delete this previous case. Now we'll run the current case. Just wait for a while. If any error comes, it will solve here. Now it's showing some error. Now we'll read the error. You define a load with aperture meca on a type thermic model. This is not possible. Here you can see aperture load ST fixed 1 and fixed 2. That is, you have defined the thermal solver, it seems. Read the message file again. You define a load with aperture meca and type of thermic model. This is not possible. Yes, while defining the load, the model has to be changed. Just go here. Here you can see the model is just I have not modified. So the model has to be model ST. Just apply. That is the error. Okay, just save this file. Now just delete this file again. Now we'll run this case. So for the mechanical load, we have to define the mechanical model. For the thermal load, we have to define the thermal model. So now we have made a mistake in that. Now we have modified it. Now we'll solve this case. Now see, it is solved and saved the results. So there is no error. Now we can open this file. We'll check the results. Just go to the paraview. Just open the result file, pictures, code aster, first one. So this is our file. Just open it. Here you can see we got both the thermal result as well as the structural results. First we'll see the thermal results. Just apply. Just go to the thermal data. So this is the correct one. Now we just move into the structural analysis data. Oh, it is crashed. Now we'll open it again. Now just directly go into the paraview. Just open the file. Just apply it. Just move into the displacement. So this one is the displacement magnitude. And we want to see the stress value. This is the sigma xx. Here you can see we are getting the compressive stress. That is because of we are arresting the expansions. If you want to see the deformed shape, you just apply here. Give some scale value, just apply it. So this is the way it is going to behave. So see the stress value in the blue to red rainbow color. We can simply just modify it here. So this is the way we can check it. This is the sigma yy value and sigma zz value. So in this tutorial, we have learned how to create the setup step by step using aster study module in thermomechanical analysis. So thank you for watching my videos and click the bell button for more notification. Thank you.